Okay, this is a section from chapter 18, but we're going to cover this because it's in the course outline. So this is section 18.2, balancing oxidation-reduction reactions. We've talked about what oxidation-reduction reactions are. Oxidation is an increase in oxidation state. Sorry, that just cannot be read. That's wrong. I don't know why I like green, but I do. Oxidation is an increase in the oxidation state. Reduction is a decrease in the oxidation state. Another way to remember this is oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. So if we look at the reaction between calcium and water, we see that calcium goes from an oxidation state of 0 to an oxidation of plus 2. That's an increase in oxidation state, so the calcium becomes oxidized. Now, looking at water going to hydrogen and hydroxide, it's not real obvious what's going on, what's being reduced. We have to look at the oxidation states. Here, hydrogen is +1, oxygen's -2. And over here, oxygen's still -2. So nothing is happening to the oxygen, but the hydrogen, one of them is staying the same and another is going down in oxidation state. So the hydrogen is being reduced. You have to have oxidation and reduction occurring together. If one thing is losing electrons, another must be gaining, and vice versa. When we balance an equation, the mass must balance and the charge must balance. Oxidation-reduction reactions can be almost impossible to balance by inspection. And so we use a different method to balance them. We break the equation into two half reactions, one for the oxidation, one for the reduction. We balance those individually and then add them back together. In case you're rusty on your oxidation states, the rules for assigning oxidation states are in order of priority. So if you get a conflict between two rules, you go with the higher numbered rule. So free elements have an oxidation state of 0. Monatomic ions, the oxidation state equals their charge. The sum of the oxidation states in a compound is 0 because the charge on the compound is 0. The sum of the oxidation states in a neutral molecule is 0, or in a polyatomic ion it equals the charge. So a lot of times oxidation state and charge are the same, but that's it's not exactly a coincidence, but it's important to remember that oxidation state is not the same as ionic charge. In compounds, metals are going to always have positive oxidation states. Group 1 is going to be +1, group 2 is going to be +2. So those are pretty easy to remember. And then the one that takes a little work to memorize is the nonmetals. So we have this order here: fluorine, hydrogen, oxygen, and then 7, 6, 5. So fluorine gets to be -1, hydrogen gets to be +1, oxygen gets to be -2. Those oxidation states correspond to the preferred charges that those elements would have as monatomic ions, but we have to assign them in order of priority. Any questions yet? Should be review. So here's the procedure for the half reaction method. Assign oxidation states to all the atoms, identify what's being oxidized, what's being reduced. Then we separate the overall reaction into two half reactions. One for the species being oxidized, one for the one being reduced. You're going to balance each half reaction with respect to mass. First, you balance all the elements other than hydrogen and oxygen. Then you balance oxygen by adding H2O to the appropriate side. Then you balance the hydrogen by adding H+. Bless you. Next, you balance each half reaction with respect to charge by adding electrons. So the sum of the charges on both sides of the arrow has to be equal, and you make up any difference by adding electrons as needed. Now you've got two balanced half reactions, but the number of electrons transferred from the one has to equal the number accepted by the other, and so we need to get the same number of electrons in both half reactions. So you may need to multiply one or both of the half reactions by a small whole number. Then you add them together, the electrons will cancel out, and then double check that everything's balanced. So let's do some examples. So let's balance this redox reaction. And for these first couple, I've listed just short version of the steps over here. So the first thing we have to do is assign oxidation states. What's the oxidation state of aluminum? Zero. So this is 0. What's the oxidation state of Cu2 plus? 2. It's plus 2, same as the charge. Over here, aluminum 3 plus. I could start calling on people by name. What's the charge on aluminum 3 plus? Thank you. Plus 3. And how about on copper? 0. Now we're going to separate this into two half reactions. So the aluminum is going up in oxidation state. It's being oxidized. The copper is decreasing or being reduced in oxidation number, and so that's the reduction. So here we've got the first one, we'll do aluminum going to aluminum 3 plus. So that's 1. And then we've got copper 2 plus going to copper solid. Okay? Then we need to balance with respect to mass. Elements besides hydrogen and oxygen first. So is this one balanced with respect to mass for aluminum? Yeah, this is 1 on each side, right? And the copper equation is balanced also, 1 on each side. Next we balance oxygen and hydrogen. There aren't any, so we're done with that one. We didn't have to do anything. Next we're going to balance with respect to charge. The total charge on the left side of the arrow here is 0, and the charge on the right side is plus 3. That's not balanced. We can add electrons to balance the charge. If we add electrons to this side will become negative, that side will become positive, and that makes it worse. We need to add electrons to this side, and so we'll add 3 electrons over here. Now the total charge on the right is 0, the total charge on the left is 0. Down here, what side are we going to add electrons to? The left side, the reactants. So we need 2 electrons over there, balanced with respect to charge. But when this reaction occurs, we can't have this one giving up 3 electrons and this one only gaining 2 electrons, because what happened to the other electron? So we need the numbers of electrons to be the same. Well, 3 and 2, we're going to go for the lowest common multiple. We're going to go for 6. So we're going to multiply this by 2, and we're going to multiply this one by 3. And I'm only putting the 3 at the end because I didn't plan ahead and there's no room on the left. So I'm going to just switch colors and write it all out. So that's 2 aluminum going to 2 aluminum ion plus 6 electrons. Just carrying through the tube. I'm sorry. Yeah, it is a tube. And over here, I'm going to have 6 6 electrons plus 3 copper ions going to 3 copper atoms. When I add the two orange equations together, this one has 6 electrons as a product, this one has 6 electrons as a reactant. Those are going to cancel out. So I add the orange ones. These guys go away. So I end up with 2 aluminum plus 3 copper. And I realize I've suddenly dropped the state symbols. 2 aluminum, 3 copper, and that's going to give us 2 aluminum ions and 3 copper atoms. So this is our balanced equation down here. Step 7 is verify. Check. I've got 2 aluminums, 3 coppers, and total charge I've got 6 plus and 6 plus. Any questions? The way it was written up here, you look at that and you say, oh, well, that one's balanced already, right? It's mass balanced, but it's not charge balanced. This is a very simple one, and so you could probably figure out how to balance that by charge. But when they get a little more complicated, it can be pretty tricky. No questions? Let's do another one. So this one says balance the redox reaction in acidic solution. There's 2 types of solutions. There's acidic and there's basic. Generally, it will tell you. If it doesn't, I guess you would probably assume acidic. And we'll go over what the difference is with the basic in a minute. So let's do this one. First, we're going to start by assigning oxidation states. What's the oxidation state of H+? +1. So this is +1. How about chromium? 0. It's an element. How about H2? 0. It's also an element. And think about it. You've got 2 hydrogen atoms. Their oxidation numbers have to add up to 0. Why would one be +1 and the other be -1? There's no reason for that to happen. They must both be 0. Cr2 plus, that's a +2. So we've got our hydrogen being reduced and the chromium being oxidized. And so we're going to separate those into 2 half reactions. Let's see if I can leave more appropriate space this time. So H plus aqueous is going to go to not H2O, H2 gas. And we're going to get chromium solid going to chromium ion. Separating into 2 half reactions. Then we're going to balance them with respect to mass. Other elements, oxygen, and then hydrogen. Well, this one doesn't have any other elements, and it doesn't have oxygen, so we'll just balance the hydrogen. So here we've got 2 hydrogens, and here we have 1 hydrogen ion. So we can just put a 2 in front of that, and that's now balanced with respect to mass. This one, chromium to chromium ion, is already balanced with respect to mass. Next is charge. So here we've got a +2 charge on the left and a 0 on the right. So we need to add 2 electrons. And that corresponds with the oil rig mnemonic, right? Reduction is gain of electrons. The hydrogen is being reduced, it's gaining electrons. So we're adding electrons to the hydrogen ions. And oxidation is loss of electrons. The chromium is being oxidized, it's losing electrons. To charge balance this, we have to add 2 electrons to the product. Everybody okay with that? This one now, we've got 2 electrons here and 2 electrons there. We don't need to do any multiplying because we already have the same number of electrons on each side. So we can just add these together. And the electrons are always going to go away when we do this. And if they don't, you need to go back and do the steps again. 2H plus aqueous plus chromium goes to H2 gas plus chromium ion. Any questions? That was also a pretty simple one. Let's look at this one. This one's a little more complicated. If you try to balance this one by inspection, here you've got oxygen on the reactant side, and there's no oxygen on the product side. So that becomes an immediate problem of what to do. So first thing is assigning oxidation numbers, oxidation states. Fe2 plus 2, the charge on a monatomic ion. Permanganate, let's skip that for a minute. Here's iron 3 plus, so that's a +3 oxidation state, and manganese 2 plus, that's a +2 oxidation state. So those were easy. It's this permanganate ion. So the permanganate ion, we know that the oxidation numbers of the manganese and the 4 oxygens have to add up to -1. So the manganese is going to have an oxidation state equivalent to its ionic charge, but we can't really figure that out just looking at this. Oxygen is going to get to be -2. So the oxygens are -2, and from that we figure out what the manganese is. So we have 4 oxygens. So there's 4 times -2. That's -8. And these have to add up to -1. We're going to call the manganese X. So X minus 8 equals -1. The manganese must be +7, right, in order for this overall to have the oxidation numbers add up to -1. So the manganese is +7. Any questions about that? Some of these ions some of these metal atoms have oxidation numbers that are kind of high. +7 seems kind of high, but it does that. So we got our oxidation numbers, oxidation states assigned. We see that iron is being oxidized and the manganese is being reduced. The oxygen, well, the oxygen doesn't show up as a product yet, so we're not going to worry about him. But we're going to put the iron in an equation by itself and the manganese. Let's see. So we've got Fe2 plus. I'm going to leave the the phase state symbols, state symbols out for now. So we've got Fe2 plus going to Fe3 plus, that's 1. And then I've got the permanganate going to manganese 2 ion. Balanced with respect to mass and then to charge. So this one's already balanced by mass, 1 iron on each side. Here the manganese is balanced, but the oxygen isn't. We're going to balance oxygen by adding water. So we've got 4 oxygens on the left side. That means I'm going to add 2 water molecules. No, 4 water molecules. 4 water molecules to the right side. So I can get 4 oxygens. Well, now that throws hydrogen in there, right? So we'll balance the hydrogen with H+, because this is acidic solution. So I have 8 hydrogens on the right side. That means I need 8 hydrogen ions on the left side. Now, maybe it seems like cheating or something to throw water in there, right? But this is happening in aqueous solution. There's lots of water molecules in there, right? And if it's in acidic solution, that means there are some hydrogen ions present. And so throwing those in there isn't really a problem either. So we're balanced for mass. Now we fix up the charges. So here we've got +2 and +3. Well, we need to add an electron over here, right? If we add 1 electron as a product, now we've got a total +2 charge and +2, and we're good. Down here, manganese, 2 plus on this side, and what's the total charge on this side? +7. We need to get that down to +2. So I'm going to add 5 electrons. So 5 negatives, 8 positives, and a negative add up to equal the +2 on that side. Does that make sense? It's one of those things you could make an equation for it, but that's actually more confusing than just kind of thinking about it. Now what do we need to do? To add these together and get the electrons to go away, we have to have the same number of electrons in each of these half reactions. So we've got 5 down here and only 1 up there. So we need to multiply this reaction by 5. So I'm just going to sneak a 5 in front of everything. Still balanced, but now when I add these 2 together, the electrons will cancel out. So we add them back together, the electrons cancel out. So I'm going to get 8 hydrogen ions. I'm going to put my state symbols back in. And I've got 5 iron 2 ions and a permanganate ion. And then I've got 5 iron 3 plus ions and a manganese 2 ion and 4 water molecules. And that will have a state of liquid. Then you should go through that and double check and make sure that the charges are the same on each side of the arrow and the numbers of atoms of each kind. Any questions? Do one more acidic one. Copper and nitrate going to copper ion and NO2. So elements have oxidation numbers, oxidation states of 0, and monatomic ions have oxidation states equal to their charges, so that's good. Here we have nitrate ion. This is 2 nonmetals, and so we're going to the little table which went fluorine, hydrogen, oxygen, and it finally just came back to me. I knew there was something. I went over this with my 3A class. The order is FHO and then 765. The 765 is pretty easy to remember. It's the FHO. So that reminds me of those awesome noodle places, right? Pho, PHO. PH makes the F sound, so kind of. Pho, noodles. If you think of noodles, maybe you can remember that. If that works, great. If not, figure something else out. So oxygen comes before nitrogen. Nitrogen's in group 5. So the oxygen gets to be what it would have for a charge as a monatomic ion. So the oxygen gets to be -2. Then what is the nitrogen going to have to be so that the oxidation states add up to -1? +5. We've got -6 from the 3 oxygens. We need a +5 for the nitrogen to give us that -1. So that's pretty different from nitrogen's preferred ionic charge of -3, but that's okay. And then we're going to do the same process over here. Again, oxygen has priority over nitrogen. It gets to be what it wants. That's how I think of it. It gets to be -2. There's 2 of them. That's -4. So what's the nitrogen then? +4. So what's happening here is that the copper is being oxidized. It's increasing in its oxidation state, and the nitrogen is being reduced from +5 to +4. So we'll split this into 2 half reactions. So we've got copper going to copper ion, and then we've got the NO3 minus going to NO2. The first one's already balanced with respect to mass. The second one is not. So the nitrogens are okay, but we have 3 oxygens on one side and only 2 on the other. How do we balance oxygen? We add water. So if I add H2O to this side, now I've got my 3 oxygens on each side. And then how do I balance the hydrogen? H plus, right? So I'll add H plus to this side, and I need 2 of those. The next thing is to balance by charge. So this one needs 2 electrons over here to make the charges balance. And the one on the bottom, the right side has a 0 charge, and the left side has a +1 charge. So we only need 1 electron down there. I'm balancing the total charge on the left side of the arrow has to equal the total charge on the right side of the arrow. I need to multiply this bottom one by 2 so that I get 2 electrons that will cancel the 2 electrons in the other when we add them together. So So I'm going to multiply by 2. So that's going to be 2 of those, and this will change to a 4. I'll have a 2 here, and a 2, and a 2. And then add them together. So the electrons cancel out. So I'm going to get 4 hydrogen ions. And 2 nitrate ions. And I inadvertently mixed up the order. But it's like adding. 2 plus 3 is 5, and 3 plus 2, also 5. The order is not real significant. And mastering chemistry actually gets that. It doesn't give you problems about order. It gives you plenty of trouble about other things, though, doesn't it? All the details, oh my goodness. And always go over it and make sure you've got the right numbers of everything and the charges add up, and that looks pretty good to me. Okay? Well, what if you don't have acidic solution? What if you have a basic solution? One extra step. So you balance the other elements besides hydrogen and oxygen. You balance the oxygen by adding water. You balance the hydrogen by adding H+. One extra step for basic solution. Basic solution, you're not going to have hydrogen ions floating around. And so we need to get rid of those. And so we'll neutralize those by adding enough of the hydroxide ion to neutralize each hydrogen ion. So if you have 2 hydrogen ions on the left, then you'll have to add 2 hydroxide ions on the left. And when you add hydroxide and hydrogen ions together, they'll make water. If you add hydroxide ions to one side of the equation, you have to add them to the other in order for it to stay balanced. Okay, so let's do a couple of examples of that. Balance this one in basic solution. So we'll go through all these same steps. First, oxidation numbers. What's the oxidation state for iodine minus? -1. In permanganate ion, what does the oxygen get to be? -2. And so then what is the manganese? +7. We did that one before. What's the oxidation state for iodine as I2? 0. And MnO2. Well, the oxygen gets to be -2, and then we figure out what the manganese is. Must be +4. So now we separate. We've got iodide being oxidized to iodine. It's increasing in oxidation number. And the manganese is being reduced from +7 to +4. So we've got I- going to I2. And we've got MnO4- going to MnO2. Balance for mass first. So here I've got 2 I's on the right. I only have 1 on the left, so I need a 2 there. Down here, I've got 1 manganese on each side, 4 oxygens on the left, only 2 on the right. So I add 2 water molecules to balance the oxygen. Then I need to balance the hydrogen. balance the hydrogen by adding H plus ions, just like we did before. So 4 hydrogens on this side means I need 4 hydrogen ions on the left side. So 4H plus. But now, because this is basic solution, I can't have H pluses. So what I'm going to do is I'm going to add 4 hydroxide ions to this side, because those will effectively neutralize the hydrogen ions. If I add 4 to that side, I'm going to add 4 to this side. So these guys combine together to make 4 water molecules. And I've got 2 water molecules over there. So those 2 will take out those 2. And so I've got 2 waters on the left and none on the right. And that's kind of a mess, isn't it? So let's write it again. 2H2O plus MnO4 minus going to MnO2 plus 4 OH minus. Any questions? Got our mass balance. Now we need to take care of charges. In the iodine, I've got a -2 charge on the left, so I need to add 2 electrons to the right. And down here, I've got -1 on the left, -4 on the right. So I need 3 electrons over here. I need to adjust my coefficients so that I have the same number of electrons here and here. Right now I have 2 and 3. So I'm going to multiply this whole equation by 3. So that's going to be times 3. So this becomes a 6, and this is a 3, and that becomes 6. That's not a very good 6. And down here, I'm going to multiply this one by 2. So the 3 becomes a 6, and this 2 becomes a 4, and that's a 2, and this is a 2, and this 4 becomes an 8. I dare you to do this without writing something down. Those of you who don't like to show your work. This is one where you really just should write everything down. So now I'm going to take this equation and add it to this one. This guy in the middle is not needed anymore. So we add these together. So we've got 6I minus. I'm going to leave the state symbols out because I don't know if I'm going to have room for them. Plus 4 water plus 2 MnO4 minus. And that's going to give us 3I2 plus 2 MnO2 plus 8 hydroxides. Any questions? One more and we'll call it a day. Well, lecture-wise anyway. Here's another one. Balance in basic solution. So here we have hypochlorite ion. We have nonmetals, and we think of noodles, and we have FHO, and then 765. So oxygen comes before chlorine in priority. So the oxygen gets to be what it wants to be, which is -2. I think of the nonmetals as wanting to have an oxidation state equal to their charge as a monatomic ion. So that's why I'm saying oxygen wants to be -2. So if oxygen's -2, then the chlorine must be what? +1. Here we have chromium hydroxide. This is an ion. We didn't really learn how to name that. It's a complex ion. I think it's, well, never mind. They go over that in 1B. We're going to go to the nonmetals here because chromium is part of a polyatomic ion here, so we can't just pick a number for it. So here, hydrogen gets its preference. Hydrogen wants to be +1. Oxygen wants to be -2, and chromium takes up the slack. So this combination gives us -1, right? And there's 4 -1s, total of -4. The overall charge is -1, and so chromium needs to be +3. If that didn't make any sense to you, you can work it out in a way that does make sense to you. Over here, chromate ion. So again, the oxygen gets to be -2. So that's a total of -8. The oxidation states have to add up to -2. So the chromium is +6. And then chloride ion is -1. So we've got chlorine going from +1 to -1, so that's reduction. And we've got chromium going from +3 to +6, that's our oxidation. So ClO minus going to Cl minus. And then we've got CrOH4 minus going to CrO4. What a mess. Start that one again. Assign oxidation states, write 2 half reactions, balanced by mass, then charge. So here we've got 1 chlorine on each side, that's fine, but we have an oxygen on the left and none on the right. So we're going to balance that by adding H2O. That introduces hydrogen, and so we're going to have to put 2 H pluses on the left side to balance the hydrogens. Then we remember, oh, this is basic solution. I've got 2 hydrogen ions here. I need to add 2 hydroxide ions. And if I do that on that side, I need to do it on this side, 2 hydroxide ions. Well, these guys combine to make water. So I'm going to take those and rewrite them as 2H2O. And then we're going to look at this and say, well, 2 waters on that side, 1 on this side. I really don't need this guy at all. And I'll get rid of that coefficient. So now I'm balanced for mass. Let's just go ahead and finish this guy with charge. -1, -3. So I need electrons on the left side. I need 2 electrons over here. And I'm just going to move this guy over because he's off in left field, or right field, actually. Okay? On the bottom here, chromiums are balanced, the oxygens are balanced, but the hydrogens aren't. So I've got 4 hydrogens on the left and none on the right. So I'm going to put 4 hydrogen ions on the right. Basic solution, so I have to add in, I look at the number of hydrogen ions that I have, and I add that number of hydroxide ions to both sides of the equation. Then I look at this and I recognize that 4 hydrogen ions and 4 hydroxide ions make 4 water molecules. And so I'm going to rewrite that. As 4H2O. Then I have to look at my charge balance. I've got -4 and -1, total of -5. And over here I've got -2. So if I put 3 electrons in there, then I'll have -5 on both sides. I need to add these two back together. They're half reactions. I need a whole reaction. But when I add them together, I need the electrons to go away. And so I need to get these numbers the same. I've got 2 here and 3. And so I'm going to multiply this top one by 3. So that becomes a 6. There's a 3 and a 3 and a 3, and this becomes a 6. I'm doing that so I can get 6 electrons. And then down here, I want 6 electrons. I'm going to multiply everything by 2. So I'm going to get 8 of those, and 2, and 2, and this becomes 8, and this becomes 6. And then I'm going to add them together. The electrons are going to cancel out. Are there some other things that are going to cancel out on this one? Or partially? The hydroxide's in the water, right? There's different ways to do this. You can add it all together and then cross stuff out, or you can kind of be preemptive and cross stuff out ahead of time. I've got 3 water molecules here, and I've got 4 over there. So 3 of them are going to cancel out. So if I cancel out 3 of the 8, let me throw another color in here. That's going to leave this with a 5 and none on that side. Hydroxides, I've got 6 over here and 8 over there. So 6 of them are going to cancel out. That's going to leave me with 2 there and none over here. If it makes more sense to add them together and then take those guys out, by all means do that. So now I'm going to add these up. And I'm going to get 3 ClO minus plus 2 hydroxides plus 2 CrO4 minus. That's going to give me 3 Cl minus plus 2 CrO4 2 minus plus 5 H2O. See, 8, 9, 10 hydrogens on each side, 3 chlorines, 2 chromiums, 8 and 5, 13 oxygens on the right, 8, 4, 5, yeah, balances. Any questions?